Hello, everyone. I guess I got a false start, so I'll start from the beginning. Thank you for joining us on this Vapor tutorial. This is the first time we've done a Vapor tutorial that's been 100% purely live. And so one of the things I want to point out is that if you're here and you're watching the live stream, there should be a link at the bottom of the video to a website called Slido. If you click on that link, you'll be able to submit questions to the rest of my team. My teammates, John, Sam, and Stosh, are available to answer questions through a chat-esque interface. And if the question is big enough, they can ping me to address the question mid-presentation. But what I'm anticipating doing is having about 45 to 50 minutes of Vapor demonstration and then having 10 to 15 minutes of Q&A at the very end. So moving on to the next slide, what is Vapor? Vapor is a desktop application, and it's open source and it's completely free. You can download it and install it at this website down here, www.vapor.ucar.edu, and it's cross-platform. You can use it on Linux, which we support CentOS, Red Hat, Linux, Ubuntu, as well as Mac OS X and Windows. The goal of Vapor is to make visualization easy for not just geophysicists, but geoscientists, astrophysicists, atmospheric scientists, and anyone working in those rough scientific domains. We believe that scientists should be focusing on their science and not breaking their backs trying to learn new tools for 3D visualization. In this tutorial, we're going to talk about how to use Vapor and its renderers. I mentioned earlier that Vapor is a desktop application, and it's comprised of 10 things that we call renderers. Each renderer can take your data and depict it on your screen uniquely according to different parameters of color and opacity. So I'm going to try to plow through about 7 if we have time, but there's a total of 10, and we're going to try to get through as many as we can. If we do have time at the end, I'm also going to talk a little bit about how to get your data into Vapor, which may or may not pertain to you based on your data format. Before we go on, though, I want to take a minute to talk about visualization in general and how we've been doing visualization since the dawn of humankind. This picture on the right is considered to be the first flow visualization that's ever been done in history, and it was done in the late 1400s by Leonardo da Vinci. This picture is called Da Vinci's Bubbles. And shortly after Da Vinci, Newton published Principia Mathematica, and this is the era that I consider to be the dawn of modern science. And the fact that we were doing visualization along with the development of calculus kind of indicates to me that visualization is an inherent part of science. And so if we move forward in time, we move into the age of computing. On the left, we see a picture of Warren Washington looking at his visualizations on a piece of camera film that was taken with a device that you can see on the top right. That device is called the DD80, and it's really just a glorified camera taking pictures of a computer screen. You can see the simple visualization that they were producing on the bottom right. And if you look at Warren's face, you can see that even these simple visualizations are telling the story of his science. So since the dawn of humankind, we've been doing visualization. Since the dawn of science, we've been doing visualization. And since the dawn of computational science, we've been doing visualization. But where does that bring us right now? On the top left, you can see Warren looking at his film again that was produced, the model was produced on the Cray 1 supercomputer, but now we're using much more powerful machines like Cheyenne, much more powerful clusters. So what comes with more powerful computers? More data. And in the scientific domains that Vapor is interested in, this means that we typically have more dimensionality. We're not looking at these 2D grids that we can see on the top left. We're looking at very complex 3-dimensional grids. So what tools do we use these days to visualize 3D data? 2 of the biggest hitters in the field of 3D visualization are applications called Visit and another one called ParaView. And these are tremendous applications. They consistently win awards in visualization contests and are consistently used to publish complex scientific 3D data. But if we take a little bit closer look at ParaView, we can see it's extremely complicated. There are 1, 2, 3, 4 top level menus. I don't know if you guys can see my cursor, but I'm counting 4 top-level menus, a large panel on the left, another control panel on the right, and even the central visualization window has its own menus embedded into it. My argument is that this is Vapor's strength. Even though we can't do things like in situ visualization and parallel visualization yet, we offer a easier user experience so that scientists can focus more on their science and less on learning new tools. This is Vapor's basic user interface. There's one top level menu and a control panel on the left, and then our visualization window on the right. The 3 main components in Vapor to pay attention to, I've labeled under here 1, 2, and 3. Number 1, this is our parameter control window. This is where you'll be setting all the parameters that determine how your visualization appears over here in panel number 3. It consists of 4 tabs, and I'll go through those in a minute. But before I do that, I want to talk about section number 2. This is what we call our render holder. This is a table of the renderers that you have instantiated and turned on or off with these checkboxes up here. So one more time, Vapor has 10 renderers, and you create and enable them up in this window over here. But the thing you'll be interacting with most of the time is this panel on the lower left. Here we can see that there are 4 tabs: variables, appearance, geometry, and annotation. But variables, appearance, and geometry, those are the big 3. Those are the ones you'll be interacting with more than anything. And they associate with what, how, and where. So variables determines what you're looking at. What variable have you selected? And in this case, we can see we're rendering our QCloud variable. The appearance tab is how you're rendering it. And this is actually the heart of Vapor. This determines how color and opacity are being applied to the variable that you selected in the variables tab. And the transfer function that we see right here, this is, I don't know, this is the heart of Vapor. It determines, we can see a distribution of our variable right here, this histogram, and the colors are being applied to your variable according to this color bar. And again, I'll be going through this interactively. It might make more sense than me jumping through it right now. But the point is, the transfer function determines, it's a filter. It filters your data so that you can see through your 3D volume. If we didn't filter your data, we would be seeing a brick right here on the right. In other words, if we didn't omit any of the data values, if we didn't filter anything, we would just be seeing a big wall at the front, a big wall on the top, and we wouldn't be able to see through into the eye of this hurricane because all the data would be shining as bright as every data value, and we wouldn't be able to see through into the field. The last tab is geometry, and again, that associates with where, and basically that allows you to select different regions that you're rendering to. If you're interested in looking at a certain region, you can restrict the data that you're selecting. So for example, if we look at our geometry tab right here, we have these sliders that determine the extents of the data that we're rendering to. In the next slide, this slider has reduced the minimum Z extent. And so what that did is it cut off the top of the hurricane, and now we can see kind of into this section of the eye wall over here. And so that's the point of the geometry tab. It can be used to select what region of data you're trying to find your observables within. Going up to our render holder, how this thing works, how you instantiate and create a new renderer depends on, well, you have to click on this new button. So when you click on a new button, you instantiate a new renderer after you select which one you pick from this dialog. So you click on new, this dialog comes down, and then here's our list of renderers that are available in Vapor. You can double click on the renderer of choice, and then once you do that, your renderer will pop up in this table over here. Once it's in this table, you can select an active renderer, and it will highlight the row for that renderer, and then the parameters for that renderer will show up in this control table. So for example, right now we're looking at the parameters for our selected volume renderer, but if I wanted to edit the parameters for a different renderer, I could click on a different row and those parameters would show up in the control panel down here. So in this lesson, I'm going to go through 7 different renderers, or try to get through them as quickly as I can at least. It's a lot to cover. But I'll first go through the slice, which is one of our simplest renderers. It's basically just a two-dimensional cross-section on an XY, XZ, or YZ plane. I'll be making an image renderer. If your data is on a lat-long coordinate system, or if it has a proj string, you can create an image renderer and just enable it, and you will have a map in your visualization. It's a very simple one to use, and that'll be really quick. The volume renderer will be an excellent demonstration of the transfer function, and an excellent demonstration of why 3D visualization is so much more challenging than 2D visualization. Again, we're going to have to filter the data in a way so that we can see through the volume and not just a plane at the front of it. So we'll be doing that by applying opacity to some of the data values. Unless we mask out and filter some of the values with opacity, we won't be able to see through the volume. The next renderer will be the Isosurface Renderer, which you can think of as a three-dimensional contour. It's basically a surface that follows a selected data value through your volume. So in this image right here, I believe I'm looking at this might be, oh gosh, this might be a pressure surface. So the surface is following one pressure value. So like, let's say I pick 50 millibars. Every point on this surface has a value of 50 millibars, but I'm also coloring it according to a secondary variable, such as temperature. So isosurfaces are useful if you are interested in seeing something like a dew point. You can make a pressure isosurface colored by temperature and see how these two variables interact with each other that way. I'll also go through a quick demonstration of our model renderer. Vapor supports 3D models, and I'll show you guys a website where you can download 3D models for things like wind turbines and buoys. I'll be I found a model file for NCAR's Mesa Lab, and so I'll be putting the Mesa Lab into Hurricane Katrina today and demonstrating that way. And then finally, I'll be going into our vector renderers. We have a Barb Renderer, which operates on 3 vector fields, typically U, V, and W, and it just shows arrows pointing in the direction of these 3 vectors. And then finally, the flow renderer, which has 2 modes. There's steady flow and, well, I guess we call them streamlines and pathlines. Streamlines are time invariant. So if you inject a streamline into a single time step, that streamline will just follow the vector field until you tell it to stop. Pathlines are time variant. So you can imagine taking a fistful of feathers, throwing them into a hurricane, and then pathlines would show you the trajectory that those feathers would take in series with your time. The very last thing, if I have time for it, is there's one section I'd like to touch on, and we might not have time for this. It's about CF compliance, getting your data into Vapor. And Vapor supports 3 different primary data formats. We support WRF ARW natively. So if you're a WRF user, you don't have to worry about this. Vapor can natively read your data. It's a piece of cake. Same thing goes for some flavors of MPass. But if you have generic NetCDF data, you have to make it CF compliant, which means adding a few attributes to your data and making sure that your grid is defined by coordinate variables. But if I don't get as far as any of this, if I don't get to any of these steps, I do want to point out, so if you go to, sorry, I'm going too fast already. If I go to vapor.ucar.edu and click on the documentation page, everything that I'm going to go through in this tutorial is described here. So if you're interested in a certain renderer, you can click on this Using Vapor 3 tab, click on the renderers, and then click on Volume Renderer. And there's going to be a YouTube video that's going to do more or less the same steps that I'm presenting right now, if not even more because of lesser time constraints. So speaking of time constraints, let's dig in. I'm going to exit out of my presentation. And I've already installed Vapor. Looks like I already have an open session. I'm going to close that. In order to open it, I'm going to go down here and just click on this V. If you're on a Mac, Vapor will install into your applications directory, just like any other application. So you can double click it that way. And on Windows, you'll probably get a desktop icon. On Linux, you might get an icon on your desktop, or you might have to execute Vapor from the command line. But now that I have Vapor open, I basically have a big transparent screen on the right, and my control panel is completely disabled. And that's because I haven't loaded data yet. So I'll click on File, Import, and I'm going to import WRF ARW data for this tutorial. And again, I think there's a link on Slido if you want a copy of this data and to go through it during the recording. So I'll click on WRF and navigate to my Katrina files. This is a WRF simulation of Hurricane Katrina. Once I do that, I get this white cube, which is the domain that my data exists in. I can right click on my mouse and drag out to zoom out and zoom back in. I can middle click to traverse the scene, and then left click is rotating the scene. And so that's how we navigate around things. The first thing I'm going to do is create my first renderer by clicking the new button, double clicking on my slice renderer, and just turning it on. And so that's my first rendering of my slice. Right now we're looking at the pressure variable, and I think that's sufficient for now. So I'm not going to change the variable I'm looking at. But what I do want to do is go to the appearance tab, because this looks very washed out. It's very light blue, complemented by very light red. And so the way I change this is back here in the heart of the vapor, the transfer function. There's a couple of things I can do. It's a left click on these color control points, and that adjusts this color value. And by squeezing these in, I can apply different color values to this histogram. So I guess I should back up. This histogram is the probability distribution of our variable. So we have this clean unimodal distribution, this witch hat. And so what we typically want to do with these witch hats is apply a color map that it diverges in between 2 points. And so this is called a diverging color map. You have blue on the left, red on the right, and then an intermediary color in the middle. So by dragging these color points back and forth, I can adjust how the color is being applied to these data values that lie directly above the color bar. So that's half of how the transfer function works. The other half is opacity. And opacity is controlled with this black bar up here. And what it does is that the higher up it is on the y-axis of the histogram, the more opaque data values are. So if I took everything and dropped it down, we go completely transparent. If I drag everything straight up, we're completely opaque. And typically what you'll want to do in these modal distributions is mask out the most populous values in the data set, but do it carefully because you don't want to miss out on any of the information that you're masking out with your data. So in order to mask out these most populous values, what I'm going to do is I'm going to make this kind of wedge right here. And, you know, maybe, well, that's the fundamentals of how the transfer function works, but this really comes into more play with the volume renderer, because right now we're just looking at a 2D slice. The volume renderer is where it's more important to mask out data values. But for example, if I want to mask out all blue values, I could just do a little impulse function right there. And then we're only looking at data values from -101 and onward. So I'm going to disable my slice function, click new again, and move on to my image renderer, click OK. And then now that I have my image renderer, I am looking at all my image parameters in the control panel. I will enable it. And here's my image. Now, it's not exactly clear where we are in the world. And so one thing that we can do in the image renderer is we can go up to this navigate drop-down box, click on the region button, and we get these control bars. So I can right click on these handlebars and drag this region out so that we can get a larger renderer than the default, which is within the domain. So now we can see the Gulf of Mexico. There's my map, and it's all good. The next renderer I'm going to do, I'm going to click on my new button and do a volume renderer. Click on OK. And this is going to be the best opportunity to really show the importance of how the transfer function works. So I'm going to zoom into my domain. I'll turn off my region mode for now, and then I'll enable my volume. And so earlier I was mentioning how without any opacity being applied, we're just looking at a big brick. We can't see through the data values at the edges of our domain. And so what we need to do is go to the Appearance tab and then apply opacity with this black bar at the top that we were talking about earlier. Again, we're looking at pressure. So we have this unimodal distribution. And so what I'm going to do is I'm going to mask out the most populous values right here at the top. And let's see, I'm going to drag this a little bit over. And this is just applying more opacity to these values. So these values at the tails, they're going to be completely opaque, but they're ramping down towards the middle at the mode of the distribution. I'm also going to bring in my color so that this span, this color transition, highlights the two tails of the histogram in more of a contrasting way. Another thing I can do, which I'm going to go to my variables tab, and I'm going to click a different variable. This one's called QCloud. And once again, once I change the variable, our transfer function is reset, and we have this big brick of one color. I'll go to the Appearance tab, and here's my distribution of my variable. So my most populous value is over here on the left. If I just drag this down and I mask out most of the values, then I can actually see into the domain. But this color map we're using is what's known as a diverging color map. It goes from blue to an intermediary color into red. And for distributions like this, when you don't have a witch hat pattern, it's usually best to use what's called a sequential color map. So to change my color map, I'll click on this toolbox. I can go down to Load Built-in Color Map, and we have some built-in diverging, highlighting, and sequential color maps. Let's see, if we're looking at clouds, I think the rain color map is a good selection, so I'll click on rain. And I don't know, that doesn't look too great, but one thing I can do is, the reason this doesn't look too great is because most of our data values are over here on the left, and I could drag the extents of the transfer function over, but we're still not able to see through these most populous values on the left. So I'm going to drag this over and right click on the color bar. I can reverse the color map. And then what I'm also going to do is I'm going to delete this opacity control point and this opacity control point. And then we have a very simple opacity histogram. And I can mask more colors out if I need to, or less. So there's an example of the volume renderer. And again, we go into more detail on this in our YouTube video. So check out our documentation if you'd like to see a more descriptive instance of our volume renderer, but we're running out of time. There's a lot of other options to use down here, but I just don't have the time to go through the different like ray tracing algorithms and all the other doodads that we offer. So the next renderer I wanted to go through is a very similar one to the volume renderer. It's called the Isosurface Renderer, and I'll click on New, and I'll click on Isosurface, click OK. And one of the difficulties with 3D visualization is that things can get very busy. And so what I'm going to do is I'm going to turn off my volume renderer to make room for my Isosurface renderer. Click on that row, turn it on. And the default variable is again pressure. Let's stick with pressure for now. So what you want to do with an Isosurface renderer in most renderers is go to the Appearance tab, and you can see here we have our transfer function, but there's no color bar. By default, our isosurfaces are colored by a single color value, and the isosurface is, again, it's a surface that's it's touching every single variable value at a specific point. So if I click on this widget down here, this little arrow, we can see that we currently have an isosurface of negative 520 millibars. I can drag this along the histogram to get different isosurfaces that touch those variable values. I can double click to create a secondary isosurface. So let's see, if I expand this one, then we get this kind of egg shape. And you can also apply opacity, but the opacity in the Isosurface Renderer is a little bit difficult. Let me do this. So if I scroll down, one of the powerful tools in the Isosurface Renderer is to color it by a secondary variable. So there's this checkbox down here, color by another variable. I can click that, and then I have this color map variable option and another transfer function. So now we have another distribution of pressure, and I can apply color at different values to the isosurfaces. So if I scroll up, we have one isosurface towards the right tail of the witch hat, and we're going to color that red. If I scroll up towards the left tail of the witch hat, we'll color that one blue. And this is kind of where the opacity controls for the Isosurface Renderer come into play. One thing I can do is I'll make a new isosurface right here, but we cannot see it. Let me go to the bottom, we can see through the bottom. I'll turn off the image, and you can see I have an isosurface that's encapsulated by another isosurface. And so what I can do is apply opacity to one of the isosurfaces. So let's see, if I do, which one is it? This one. I'll double click here, I'll double click here, and I'll click in the middle of the black line to bring these two down. And what this is doing is it's applying, here, I'll bring these guys in. And so what my transfer function is doing is it's applying maximum opacity to my -767 isosurface, maximum opacity to 173, which I believe is the red. But this one here in the middle, I can mask in and out and give it some level of opacity so that we can see through the isosurface. So that was the isosurface. Let's move on. I'm going to turn the isosurface off, turn the volume rendering back on, and the next renderer will be the model renderer. So I clicked on new, my dialog comes down, and I'll click on model. I'll click on OK. And I have a model file of NCAR's Mesa Lab that I downloaded, so let me go find that. And one of the things about importing 3D models is that the coordinate system of the model is never really going to be the same as the coordinate system of your simulation. And so if I turn my model renderer on, it's not going to show up because the model that I'm dealing with is in unit coordinates. The coordinates of these triangles in this model go from 0 to 1, but the coordinates of this simulation go like from some negative to positive millions of meters from the meridian and equator. And so whenever you import a model, what you're going to have to do is use this transform table down here to, first of all, scale. In this case, I have to scale my model, and I'm cheating right now. I've done this ahead of time. But I'm going to scale my model by 1,000 by 1,000 on X and Y, and then Z. Now, of course, I have to turn it on. And so there's my model of NCAR. Once I've scaled it up to the size of Hurricane Katrina, there's the NCAR Mesa Lab. The second thing I need to do is translate it within my scene. And I know this is kind of a silly example, but let's see, 3,500,000. But the point I'm trying to make here is that, there are, observational sensors, wind turbines, and tons of models out there in the world that you can download and put into your scene. I know this is something that's used a lot in the large eddy simulation community for buildings. I want to make a quick mention that there's a website that hosts, it's called 3D Warehouse. It's owned by a GIS company called Trimble, and they host all sorts of sensor equipment. This is where NCAR's model, I think they use photogrammetry from satellite data to generate that model. But if you just type in NOAA, they have all these, buoys galore, and, any kind of sensor that you would like to put as an artifact in your simulation visualization, that's a good place to go. So that was 3dwarehouse.sketchup.com. Okay, so there I have my model of in-car inside the Hurricane. The next renderer I'm going to make is the Barb renderer, and in order to prevent things from getting too busy in the visualization, I'll turn off my volume renderer, click on New, I'll double-click Barb up here at the top. And then once again, just turn it on. Oh, that's interesting. I wonder if that's a... Well, they usually don't look like that. I wonder if I turn off my model renderer. Yeah, there they go. So we have a lighting bug. Interesting. So we'll have to write something on that. But anyways, if I click this home button at the top, I can go to my default view, which is looking from the top down at my simulation. And here we have a series of arrows that are just pointing at, pointing along our wind vectors. So I'll click on my Barb row, and we can see my variables tab. Vapor tries to pick good default variables. And so typically wind barbs are aligned with the U, V, and W wind vectors in a simulation. These are my X, Y, and Z fields. And so if I wanted to do 2D wind barbs, I can change this drop-down menu. We also support 2D. So if I click on that, we're going to default to U10 and V10, the default variables that come out of WRF simulations. I'll go back to my 3D though, and I'll go to my Appearance tab. And the Barb renderer offers these sliders, which let you determine how many barbs you're going to put into your scene along X, Y, and Z. So I can either use a slider to increase this value to, I don't know. These are our predefined extents. I can also manually type in values. So if I do 45 by 45, I get something that looks like that. And you can see vapor kind of like slows down when you have that many barbs in the scene. But if you're looking to do something that's not aligned on the X, Y plane, so like right now we're looking at barbs on the X, Y plane, we can, let's see, I can put 0 barbs on X, maybe 1 barb on X, and then 25. Let's see what that looks like on Y. I don't know, that looks kind of crazy. But if you're, let's see, maybe Z's, maybe I can do 5. And then, yeah, max it out on 50. But if you still don't have, if our predefined slider defaults are constraining you, one thing you can do is you can right click on either the text box or the slider, and you can reset the minimum value. So if I crank that up to 500, let's see how slow I can make vapor go. No, that's not actually that bad. But I don't know, just putting that out there. If you feel constrained by these controls, you can modify it with a right click. So those are the basics of wind barbs. I guess I should also talk about, similarly to the Isosurface Renderer, barbs are by default one color. So you can uncheck this use constant color checkbox, and then you get a transfer function down here where you can go to the variables tab and pick your color map variable. And right now, by default, it's T for temperature. And so this transfer function is editable like in the other one. So I can edit the colors of the barbs according to the color bar on our transfer function. Yeah, gosh, so this is moving pretty quick. The next renderer is the flow renderer. Let's see what we can do there. So I'm going to turn off my barbs. I'll turn my image back on, and then I'll go to New and double click on Flow. And let's just turn it on. So the first thing that we see we can get is these are streamlines of our default variables. So like barbs, the flow renderer uses U, V, and W as their default variables. So that's good enough. The heart of the flow renderer has another tab that doesn't exist in other renderers. It's called the seeding tab. And this determines all the parameters for your flow lines that don't apply to their color. We apply their color and their appearance, of course, in the appearance tab. But in the seeding tab, we select our flow type. By default, it's streamlines. And like I said earlier, streamlines are just following the vector field through your domain at a single time step. They are time invariant. Path lines, I don't think I'm gonna have time to get through path lines, and this isn't the best data set for path lines, but if I do have time, it looks like we have about 20 minutes left. I might take a crack at path lines with a tornado data set. But for right now, I'm going to do streamlines. You can select your flow direction and the number of integration steps. And so if you see, I can turn that to 0. I do 1, you can see these tiny pixels, hopefully, but I don't know, 25. Yeah, it looks like that one's not an interactive controller. Maybe it is, and I just don't have the right settings. If I have a maximum value of, if I change my maximum value to 150, let's see if, ooh. Well, that's all right. Sometimes some of these renderer controls are interactive. So as you drag a slider, the renderer will change with it, but it looks like that might be a feature we can add into the integration steps at another point. But if you have too many integration steps, your flow lines are going to go outside of your domain, and so there's no point integrating past 100. But if I do 50, that's nearing the maximum limit that these flow lines will travel without exceeding the domain. There's some other controls I'm not going to touch on, but this is an important section. There's this seed distribution setting area. And right now we are injecting our seeds in a gridded fashion. So right now, if let me reduce my integration steps to 25, and that's a little bit easier to see that we're injecting seeds on a 5 by 5 by 1 grid on X, Y, and Z. And that's just one way to inject grids. You can also randomly inject seeds. And let's see, let's just, don't want to break vapor, but there's random distribution, random with a bias, so we can pick a bias variable. So if I want to, let's see, if I wanted to pick a variable to use as a bias, let's pick W, and then crank it up. And it's a little hard to see. This might not be the best example, but what this is doing is it's injecting the seeds at the high end of my variable W, if that makes sense. And if it doesn't, we have videos, once again, that do a better deep dive into these controls. Now, the last thing you can do is inject a list of seeds. So if you have a text file that specifies where you want to inject your seeds at a certain time step, you can do that too. But I'm going to stick to gridded for now. I'm going to scroll down a little bit, and we have this other section called the rake region. And if I go back up here to the top left and click on this region icon, this also, this region also lets me control where in the domain the seeds are being injected to. And so if I right click on this handlebar and drag it down, then my seeds are being injected in this tiny sliver within this red box here at the bottom. And you can see that the Z extents in my rake region have also been reduced. So there's two ways to do this. I'm injecting a 5 by 5 by 1 grid of seeds right in the middle of this red box. And so you can do it visually with the red box, or you can do it numerically with these line edits or these sliders. So now that I've dragged the region all the way to the bottom, let's crank this up to 25 by 25 by 1. Get something a little bit more interesting. Still not much going upwards, but I can left click on this box and adjust where these seeds are being injected that way, or I can do it through the region. One last thing to mention in the flow renderer is that we can write these flow lines, these locations, into a file, and we can also sample variable data along those trajectories. And so, for example, if I did, let me make 1 seed right in the middle of my domain. So this is probably right in the eye of the hurricane. If I wanted to sample the temperature variable along this streamline, and maybe the pressure variable, I can enable those two variables, write it to a file, and it looks like that was written to vaporflow.txt. So if I do vaporflow.txt, this text file will now have the location of all of these seeds, or all the location of this trajectory, and a sampling of the variables I've selected to write to the file. So, gosh, I think I have 5 minutes left before going into Q&A. I think I'd like to talk real quick about the CF conventions. So I'm going to minimize Vapor, clear this, and go back to my slides real quick. So, like I said earlier, Vapor supports WRF ARW natively. So we just saw this whole tutorial was simply importing WRF files, and you don't have to worry about any kind of data conversion if you're using WRF in some flavors of impasse. But again, a lot of people aren't using WRF and their data is in NetCDF format. In order for Vapor to read it, it has to adhere to the CF conventions. And the big motivation for the CF conventions is that NetCDF can describe so much. And Unidata, the people who are defining the CF conventions, are trying to standardize things. So applications like Vapor can have an easier time importing it. So you can read more at cfconventions.org, but what I'm going to be doing is I'm going to be working with this simple NetCDF file. I'm going to be making it CF compliant using a product called NCO. And there's 3 basic steps to doing this. CF compliant files need to have coordinate variables, which describe where the grid exists in space and time. So in this file on the left, we can see that we have 4 dimensions, X, Y, Z, and time, which is described as unlimited. The reason a lot of NetCDF files are described as unlimited with time is because those files don't know how big the time dimension is going to be. We know how big X, Y, and Z are on the grid in the entire simulation, but we don't, this individual file doesn't know how big time is going to be. We have one variable called temperature, which is based on our dimensions of time, X, Z, Y, and X. And in order to make it CF compliant, we have to make coordinate variables, which are what we see over here. So we can see once the transform is done, we have our X coordinate variable, which is just a variable that's the name that is named the same as its dimension. And this variable just describes where the X axis grid points are in space. Same for Y, same for Z, and same for time. So once we've created our coordinate variables, we need to add attributes, which describe what these axes are referring to. So this X-axis attribute describes that our X coordinate variable belongs to the X axis. Same for Y, same for Z, same for time. The last thing we'll have to do is apply a unit to our time variable. And after we do those 3 things, then we can load our data into Vapor. So I want to try to crank through this in a couple minutes. So I have a few windows open. Over here on the bottom right, I have our original file. That's what we're looking at over here. We have our dimensions, and it's a very basic, very simple file, no coordinate variables, and one temperature variable. Up here on the top right is what we're trying to get at. We're trying to build our coordinate variables and apply the attributes that I mentioned earlier. And here on the bottom left is my cheat sheet. If you guys want to take a screenshot, you can go ahead and do that. These are the NCO commands in order to make this file CF compliant. But if you don't want to take a screenshot, again, this is all in our documentation. If you go to our website and you click on getting data into Vapor 3, we have sections that describe this process under the NetCDF and the CF conventions. So I'm going to go back over, and first I'm going to use NCAP2 to create a time coordinate variable. And what that's going to do is generate what we see right here. I'm going to do NCAP2, and by the way, this is creating a time coordinate variable with a value of 1. We have an input file and an output file. And man, this is rush, but I'm going to do the same thing for my X, Y, and Z axes. And what this is doing is creating an X, Y, and Z coordinate variable that are arrays that go from 0 to 1. And the values between 0 and 1 will be applied to the grid points on each axis. So on each of our 48 by 48 by 24 spatial axes. So now we have our coordinate variables. We have X, Y, and Z. and time. But now we have to add these attributes. To add attributes, NCATED, I'm not sure if I'm pronouncing that right, but -A, I'll add an axis attribute to time, and I'll call it T. Oops. And then do the same thing for Z, Y, and X. And so then that just gives these attributes axis values so that Vapor can know what they're referring to. The last attribute we need is a time attribute to know what the units of our time is. And so NCATED-A, and basically we're assigning it an attribute seconds since 2000. And after we do that, I can go create a new session, restart Vapor that way, and import NetCDF CF compliant data. And that last file, oh, this is so fast, but that last file was simple5.nc. If I double click that, now we can look at our NetCDF data on this regular grid, create a volume renderer, and then look at the core, a very simple simulation of the core of the sun, I believe. This is a MHD simulation out of CU. So, all right, again, if that was all too fast, and I'm sure it was, the Vapor documentation, there's videos on all of this stuff that aren't as time pressed, but I'm gonna leave it there. And I guess we can open the floor to questions on Slido. So, looks like we have a bunch. How do we convert netcdf.nc file to CF format? The file contains 3 magnetic field components in time t. 2 is there. Right. So, Shushri, I'm not sure if that last section helped, but I think I'd have to, if it didn't, I'd have to point you to the documentation. So again, if you go to the Vapor documentation website and you click on getting data into Vapor 3, NetCDF and the CF Conventions, we'll talk about all this. And if you still have trouble, reach out to us over email, like our email is vapor@ucar.edu, and we can give you a hand with that. Okay, looks like Bill, free to answer this at the appropriate point in the talk. It's a great, good resource for a beginner to learn how to put homebrew data into NetCDF metadata format. Source with examples for this data would be welcome. So one thing I didn't mention, I'm not sure what homebrew data is, but there are tools in Vapor to bring floating point or double precision floating point values into Vapor. And so that I think is covered in the raw binary data section. So if you go to our documentation and look at raw binary data, if you're referring to what I think you're referring to, just like a bunch of floating point values in a file, that will be covered in this section of the documentation. But again, reach out to us, and we're vapor@ucar.edu, or you can email me at pierce@ucar.edu, and we can help you out one-on-one. Is there any way to increase? Well, I'm gonna go with this one. Is there any way to increase live stream quality, display resolution? Features not visible. Oh man. Well, I guess we are recording this and we are going to put this on YouTube. So if that doesn't fix the live stream quality, I'd have to say, look at our other YouTube videos that shouldn't have this problem. So again, I'll point that out. We have a link to our YouTube channel right down here, so I can middle click that. And we have all sorts of tutorial videos that are separate from this one, as well as other videos. So if you go to using Vapor 3, you click on the renderers and click on the volume renderer. Every renderer has a demo video that goes through the features. So I don't know, maybe hopefully that will help. Could you briefly comment? Whoa. comment about the advantages of Vapor versus other options to work with WRF. Oh yeah, okay. I got a text. Let me answer this question real quick. Advantages of using Vapor versus other options. So other options for viewing WRF are going to be more complicated, like ParaView and Visit. One option to use with WRF is NC View, but that's two-dimensional. You're just going to get simple color maps on a simple slice. The advantage to Vapor is that you can directly import your data and get going that way. You can't directly import data into ParaView and Visit as far as I'm aware. Yes, save GIFs. Yeah, so I'm going to answer this one. Is it possible to save GIFs of the 3D visualization as it moves through time? And so, yeah, I glossed over that. Let me do this. I'm going to do a new session. And I'm going to re-import my data. Yeah, so if anyone noticed at the very start, I imported 3 different WRF files, these guys. And each one of those corresponds to a single time step. So what I'll do first to demonstrate this is I'll make a new volume renderer.
Scott, do you want us to share your screen for us, please?
Am I not sharing? Shoot. Can you guys hear me?
Yes, just go ahead and share your screen and it'll take over.
Interesting. Share screen, continue. Yeah, I'm not sure what happened there, sorry. So, okay, backtracking to what I've done is I've just basically reopened the original data set that I opened at the start. 3 Katrina files. I've made a volume renderer, and I'm going to make a volume renderer on my QCloud variable, turn it on, go to my appearance, and I'll mask out a bunch of the values so we can see through. So to capture images at this point, I have 3 time steps. I'm going to click on the capture menu and click on image sequence. And I have 2 options. I can store PNGs or TIFFs. I'll click on PNG. And then I will give a surname to a series of image captures. So I'll just call this test, and I will put this in my home directory, save. And so at this point, Vapor is going to begin capturing every single rendering that it does. So if I move the scene, this rendering will get captured once it completes. That's interesting. But, well, the other thing you may want to do is advance your yeah, we're stuck in fast mode. Now, this is a extremely rare bug that's hard to reproduce. But imagine that my rendering is finished right now. So I guess the point I'm getting at is that when you move the scene, Vapor will do a screen capture, but it will also do a screen capture when you advance the time series. And that's done with these VCR controls up here at the top. So if I click on play forward, we're going to move to my next time step and my 3rd time step. And I know that was hard to see. What I can do is I can turn on a time step number annotation. And so you can see I'm looking at time step 2. I'm still capturing my images. So if I go backwards, 1, 0, and then I'm going to go to capture and end my image capture sequence. And then if I go to my home directory, I have all these images that were captured as I advanced in time and as I rotated the scene. Now to create GIFs, I usually use, Vapor doesn't support MPEG encoding or GIF encoding. So I usually use ImageMagick or Convert for those tools. So those are kind of different subjects, but if you just Google FFmpeg make GIF from PNG, there's a lot of content on Google for that. Gosh, so let's see. So I'll get out of there, and I am still screen sharing. I'm not sure what happened earlier, but I'm going to let's see, bring Slido back up. Okay, is it possible to save GIFs? Yeah, I hope I answered that question for you. How can we convert NetCDF? I think I already touched on that one. Can one plot the wind speed or at a specified height using the Barb Renderer? Yeah, so let's see if I go.
Scott, you'll need to reshare your screen again.
Gotcha. Continue. I gotcha. I see what's going on. All right. So if I open Vapor back up, and let's see, if I wanted barbs at a specific height, I would first disable my volume, create a new Barb Renderer. And if I wanted my barbs to be at a height of 500 meters, I would constrain my Z coordinates at a minimum and a maximum of 500, or maybe, yeah, there they are. So these barbs would be at a height of 500 meters. If I wanted to go to 5,000 meters, I have to constrain these two ends of the Z region. So yeah, that's how I would do that. Should I go back to Slido or? Let's see, I guess, let's see. There we go. Will Vapor have a script option? Well, let's see. Let's start at the top. Can Vapor produce high quality graphics for publication? Perhaps you could show us a way to save these images. Yeah, so that's kind of what I went through a second ago. The whole screen capture functionality. So there were two options there: save image sequence, which captures every single image, but there's also an option to capture a single image. Will Vapor have script options to do work automatically? Stosh, I think, has implemented something like this, but I am not too familiar how it works. Stosh, if you could answer that question in Slido, I think you're probably more suited for that one. Okie dokie. Is Vapor compatible with NetCDF containing stretched model grids? Yes. Like is often used in high-res CM1. So yeah, recently CM1 changed their file output format to be CF compliant. So if you're running CM1, you can directly read your data into Vapor, and it's just as easy as with WRF. So you're in luck. But to your other question, yes, Vapor also can handle stretched grids, curvilinear grids, and that gets to a little bit more tricky territory. Making curvilinear grids CF compliant, but we should really make a video that talks about that question. Do you know if Vapor will have an API, like a scripting API, like something that you can call from a Python script? That's one of the big ticket items on our to-do list, but we don't have it yet. How do we add in something like a flight path from an external file? Yeah, that's kind of one of the things that I believe we should probably support. You can technically do that through the model renderer. So if your flight path can be exported as an STL file, we've done this kind of thing before, but support for observational data is something that I push for, and I'm not sure if we'll get to that anytime soon. But there are workarounds through the model renderer. Do we have a community for Vapor users where we could use that for common questions? Oh yeah. So could someone, Stosh, John, or Sam, post a link to that question post a link to the Discord forum? And we have a Discord forum, and that's kind of where we handle our user support questions, but we also take emails too. How can we add geo info like lat long to the terrain background? Yeah, let me cover that real quick. Let me see. So I will share my screen. So yeah, this is probably an area for improvement in Vapor, but we're working on a usability release. The way you add access annotations in Vapor is through this tab up here called the navigation tab. And up here you can add annotations through the annotation tab. Access annotations enabled has a checkbox. And so right now we're looking at meters from the equator meridian, and you can click on annotate with lat long values and edit the number of annotations on each axis. So that's how you do that. It's the navigation tab and the annotation tab. How can we add geo info? Okay. Yeah, well, Vapor had the script option to do the work automatically. Work in progress. Still trying to get there. Probably with something with Python. But again, I think Stosh might be addressing this to another question. This might be a duplicate, but if we don't already support it, something similar to this, then it's coming as one of our upcoming deliverables. I guess I'll just keep going down the list. Very useful tool for people wondering about CF compliance in their files. The CF checker, agreed. And Vapor, I'll just mention, is not as stringent as the CF checker. There is a little bit of a disparity between, we're not like 100% CF compliant. We just need to know units for time, access attributes, and maybe a few other things if you're working with curvilinear grids. But yeah, that is typically what I do. But whenever we get a question from a user, you know, why isn't my file working? I usually plug their file into the CF checker, and that'll help out a lot.
Hey, Scott, sorry to interrupt, but we're starting to run over. So I suggest that maybe just announce again the discourse forum. We've replied to that
Okay.
in Slido. So that's a good place for people to send follow-up questions.
Let's see if I'm not sharing my screen. Let me do that by sharing. Okay, and then get help on our forum. So everyone, if you can see my screen, this is our discourse forum, vapor.discourse.group. And I believe you can log in with an OAuth account. So if you have a Gmail account, you can just log in with Gmail and post your questions there. And so this is probably where we'll be most responsive to any of your questions that we didn't get to. Well, I guess if we're wrapping up, I just want to thank everyone for attending, and we're really here for you guys. The more feedback we get, the better we can define our requirements. And so shout out to us over email or on our discourse forum, and that'll help guide our future releases. So thanks again for attending, and we're looking forward to hearing from you.